Hello, welcome and a very good evening to our newest episode of Let's Code MS-DOS. And today I want to show you another demo scene effect, one that I first saw, I'm not sure, I think I saw it in some DOS Fractal intro or something like that. Plus I saw it in the xscreensaver in Linux back in the mid-90s. But only this year I learned that this effect actually had its roots in the Amiga demo scene, which is why we are here on Poe, the website for everything demo scene related. I'm gonna zoom in the website a bit more. And back in 1993 there was at least one demo. I think there was another which showed a similar effect, but this one here is called Banana Man by Stellar. And there is this particular zooming effect, and we're gonna watch that demo for a short bit so that you can understand more what I'm talking about here. Basically, it's back then it was called like a fractal infinite zoomer, and yeah, maybe you can call it that, but it's actually a bit cheating, but it looks very cool, and yeah, it's pretty impressive. So I'm gonna fire up the demo and fast forward to the bit that is interesting. So as you could see, it is an interesting zooming and rotation effect, and I couldn't really figure out how to do that. I found a website which implemented the same effect in pure BASIC, and then a friend of mine picked up an old archived website by someone who made a version in C basically for DOS or Windows or whatever, and that was what I used as an inspiration. And it turns out there's also an explanation by the original coders of this stuff, and on the Amiga you would use the Blitter chip, which does basically which can very fast copy rectangles over the screen. And that's what's being done here, and it's a bit complicated to explain, but in the end it's actually pretty simple what's going on here. And I've prepared a little Excel sheet, or numbers sheet in this case. And basically what we're doing is we are subdividing the screen into a checkerboard or chessboard, whatever you want to call it. Best to use something with an odd number of rows and columns. Here taking 5 by 5. I think in the code that we're looking at I used, let's see, 13 by 13, which works fine as well because it fits on our VGA screen. Let me close the emulator very quickly. But for this example we use the 5 by 5, and it consists of two separate operations. The first one is a zooming operation where we kind of zoom the image that is created in the center. In the center we just generate random pixels, and those will create the noisy pattern that we see on the outside. And when zooming out, we are copying into the destination frame buffer by shifting every tile a little bit to the center. The ones on the vertical will be these tiles here. Instead of copying directly from the source tile, we will shift it slightly to the center and take a row of fresh pixels and a couple of rows of old pixels and copy them a bit higher into the destination buffer. Same goes for the next. Instead of copying from up here, we shift it down even further down so that we have overlap with the older one, and so on. And on the diagonals we have a similar solution. We should copy ever further in. This is used to be here, and we shift it down so that we get a lot of overlap, etc., etc. Basically what we are using here are the coordinates around the center tile. The center tile is 0, 0, which you hopefully can make out a little bit here. And going to the left will decrease our x component. This is coordinate -1, 0. this is -2, 0, and the upper corner is -2, -2, etc., etc. And this is actually also the shift that we're doing in the copy operation. This leads us to copy the image in such a way that the zoom effect gets faster the further out we get, which is what you would expect from zooming into an image or going through a tunnel-like thing. The further to the image border you get, the faster the stuff is moving, because the displacement is always larger. The smallest displacement will be in this here. We only shift by 1 pixel in each direction, and then we shift already by 2 pixels in this direction from this position, etc. Maybe this is a bit too abstract, but hopefully in the code it will become clear what's happening here. The off-diagonal things are a slightly bit different, but not too much. There we shift in one direction a little bit less, so that we get something like this. But the overlap will still be there. And if we make a bigger pattern, then we have more off-diagonal tiles which behave similarly. So this is the zooming part, but at the same time we also apply a rotation, and the rotation looks like this. We just have to flip the x and y coordinates, and if we do the flipping, so instead of writing xy we write yx, or to be precise we write -yx, we get a pattern like this. So when we go to the right, we don't copy from the cell directly, and we don't go to the inside of the image like we did for the zooming, but we go slightly down actually. And for the next cell we go even further down, so that we get a slope basically in our copy operation, which looks something like this. This is just approximate, of course. And if we fill out all the patterns here on the diagonal, nothing happens. That will stay the same. We get, you can already see that, a slight rotation movement, which is actually pretty neat. And what you have to keep in mind is we don't copy pixel by pixel, but we copy rectangles, tiles. This is due to the fact that the Amiga could only do fast copies on rectangular sections. So this was an approximation to a true zoom and scaling and rotation operation by subdividing the whole image into discrete parts, which could be handled well by the blitter. On the PC, since we have to do everything in software anyway, we could do a perfect scaling and rotation, and we did the rotozoomer back a few episodes, but that had the disadvantage that it was pretty slow actually. And this discretization into tiles is actually pretty fast, and it's even fast under DOS machines, where we can use memcopy to copy whole blocks and regions of memory instead of having to do a lot of transformations. So we will do the very same approach here that the Amiga did with the blitter. There will be a lot of optimizations that you can still do in the code. My code is short and mostly readable, so that you can easily follow. But of course, as usual, there are many optimizations that we can apply. But let's look at the actual code. I'm going to put this away. I'm starting out with roughly our regular setup here. I already filled out the whole main function for you, so we will skip most of that. The important part here is we have to use two buffers, which are called frame buffer and data chunks. The name data chunks I stole from the original code, which I augmented actually. So if you compare to the original code, mine is a little bit simpler because I think there were some unnecessary things which made the algorithm harder to understand. But you can have a look at that. I will link to that in the video description, and you can compare and see where my implementation differs. But basically this is a back buffer where we collect all the distorted imagery, and after we done that, we copy it back to the frame buffer, which gets copied to the VGA memory. We We could probably copy directly from VGA memory, but I was not sure if that's fast enough. I will probably do a second video on this, where we apply a different video mode, which is very suited for this kind of effect, and there we only need the VGA memory plus one buffer. So these are the two buffers, off size, buff size, and every buffer has a width and a height. They have to be square. I tried rectangular ones, but then I ran out of the memory at some point because of the transformations. So this works only for square buffers at the moment. I think it will get much more complicated if we want to do rectangular buffers, but that's also something for a different video. The buffer width and height is basically the tile size, which I called piece size, and times the number of pieces in X and Y direction. So you can tune that here. I found that a tile size of 16 pixels and 13 pixels across in each direction works pretty well, which gives us a pretty large image on our 320 by 200 resolution mode 13. And I'm using just simple mode 13 here because we don't need no page flipping. We just need raw memory bandwidth, and I think this is the most efficient way to do that at the moment. So we allocate that, and if we couldn't allocate anything, we bail out, but that shouldn't happen. That takes only like 100 kilobytes or so of memory. Then we clear the memory by using memset on both and writing zeros to that. You can actually leave that out and start with random values in your memory, which looks nice and interesting. You can play around with that or fill them with maybe other images, like a GIF or something. And that also looks very nice because then the image gets distorted. Then we enter the graphics mode, mode 13, 320 by 200 and 256 colors. We set our fire palette. You can use any palette that you want, but that's the one I had ready from our fire experiment, and the twister and the other effects that use the same. And then we enter the main loop. This here checks if the key code on the keyboard was escape. So with escape you can quit. But inside the loop we can also read a key if it was it. And we can toggle the rotation actually. We can do a clockwise rotation or counterclockwise rotation, which is equal to rotation equals 1 or -1. And you can even turn off the rotation by setting it to 0, and then you get only the scaling effect. The zoom effect can be toggled with Z. The same goes here. We can have a zooming into the image effect. If we set the zoom to, let me check at the top, if we set the zoom to -1, then we're zooming into the image. Or if we set the zoom to 0, there's only rotation happening, or you can even turn off everything. And zoom equals 1 means we zoom out of the image, which also looks pretty interesting. And the third part is a bit magic. It's called a shift. To get the actual fractal appearance, we don't copy from the center every frame, but we randomly select a new center, which moves around inside of one tile, so 16 pixels displacement at the most, and copies from there. Doing this every frame leads to this fractal pattern. It sounds a bit weird right now, but I will show you what the effect is by toggling the shift when we got the program running. Then we call the draw Dweezil routine. Why do I call it draw Dweezil? Because the author of this demo here, this stellar group, the author who did the effect is called Dweezil, at least in the scene. In the demo scene, his real name is, oh god, I can't read it anymore. Two Finnish guys anyway. So Dweezil was his name, and so our algorithm is also called Dweezil. Then, as usual, we wait for the retrace so that we don't get any screen tearing, and we have a synchronization to the 70 frames per second of the VGA card. And then we basically just copy the frame buffer to the screen. The whole magic here is just to center the image. I won't explain that right now because you can leave that out. And the second thing that I do is I cut off the topmost row of tiles and the leftmost row of tiles. You can also skip that, and then you will see a few artifacts at the border of the screen, because during the copy operation we wrap around in the buffer, and so the left side of the buffer will contain stuff from the right side, and it looks a bit weird. This problem can be solved by clipping during the copy operation, which the Blitter does, I think, which we don't do due to efficiency reasons. It's faster to just copy that stuff, perhaps, maybe, or we would have to adjust our copy routine. Maybe I'll do that in a later part where we talk about clipping. For now we don't, and we just cut off a little bit to the left and to the top. Once we quit, we set the text mode and return to DOS. And that's it. The Draw Dweezil routine is now pretty empty, so let's start implementing that. First of all, I talked about the shift. That would be a byte variable called shift, and we already have this Boolean variable here, do shift, which is true, so we can test for that. First of all, shift will always be initialized with 0 during call here, and if do shift is true, we will just simply pick a random value between 0 and 15. So we are inside of one tile. Basically we should use p size actually here, which jitters around our center so that we get this fractal effect. Pretty simple. Then we need to fill up the center tile with random pixels. So we do something like, we go over y and x. So what I figured out is it's pretty nice to go to roughly, let's do it like this, half the tile size, so p size divided by 2, and that goes also for the x direction. Just use a variable x, which we also need to introduce up here, and that should be an integer, I would say. Then we pick a random color. Color equals random of 256, so any value between 0 and 255 will be okay. That should also be a byte value. That's the index into our palette. And then we can use our set pixel routine, and we put it dead in the center, so width divided by 2, and we need to have width defined. Do we need that later on? Let me check my notes. Actually, no, we can just use buffer width, I think, divided by 2, because that's the same thing. Plus x, actually, this is the offset, and also buffer height plus y, and the color that we just selected. This will give us random colors. And also to use buff height divided by 2, and then we should have something that we can already see. And there we have the random pixels in the center of our buffer, which is nice. Now we need to implement the whole copying stuff. And I already prepared a function in our VGA code. You can check this out. I will not go into much detail. It's called memcopyRectangle, and it basically copies from a source to a destination with a certain width and height, and a source and destination coordinate, and the size of the rectangle that we want to copy. The width and height just tells us the height and width of the whole buffer, while the copy width and copy height gives us the rectangle. This is pretty simple stuff. It's just a bunch of memcopy calls that go line by line and copy bits or slices of the memory, basically. You can have a look at that. It's really basic stuff, and I think we probably already had something like that in one of the games, the Pong game maybe. So going back to the main code, what we have to do now is to iterate over all the pieces actually. So we go from 0 to number, what did they call it? Num pieces in Y direction. And the same goes of course for the X direction as well. Oh, come on. So X direction, same value except num pieces X. At the moment that's always the same, but maybe we are gonna fix that in a future episode. Who knows? Or you can do it at home. Alright, so first of all we need to compute the source coordinates basically for our memcopy rect, and I call this xs for x source, and these variables will be xs, x source, y source, x destination, and y destination. These are the variables that I'm going to use, and the basic tiles will be x times piece size. And we can copy that 4 times because selecting the appropriate tile is basically just our x coordinate times the size of the pieces of the tiles. And the same goes for the destination address. So this is very simple, and it will do basically nothing particular to our picture. In the end we can copy back what do I want? No, first of all I want to do the memcopy rectangle. We copy now to the back buffer, so we copy 2 data chunks from our frame buffer with the buffer width and buffer height for both, and with the source coordinates and the destination coordinates, which is basically just a simple copy. It does nothing right now, and we copy exactly 1 tile at a time. We won't see anything now because it ends up in the back buffer, but we will now copy it back to the frame buffer, the distorted version basically, or right now it's undistorted, but this is just a check that we still get the same picture that we got just now before we did that. So the target will be frame buffer, plus in theory we should use a shift, but it's not implemented yet, so that will come later, with the source being data chunks. And how much do we want to copy? We want to copy buff width times buff height pixels, because that's the whole buffer. That should compile with 1 warning due to shift not being used. We didn't implement that yet. And that gives us exactly the same output. We copy once to the back buffer and then to the other buffer again. Okay, so I had a very small bug here. It said less or equals, so I copied a bit too much and the DOS box crashed, but no worries. We fixed that. Of course, we can only go from 0 to num pieces y minus 1, so that's why we have the less than and not the less or equal. But never fear, next part is the shift, and we can just apply that to the x and y source coordinate to copy a bit jittery. This will look slightly weird and it will go off into the distance here. So we have to actually apply that to the target copy as well by applying this to the x and y coordinate, which just means the x-coordinate is plus shift and the y-coordinate is plus shift times buffer width. And to be honest, we probably should subtract the whole stuff here from the number of bytes that we copy, just not to run out of the memory that we allocated. And that will give us a steady picture because it will copy jittered into the back buffer invisibly and then undo the jitter when copying back. So we get a steady image back, which is important, otherwise it looks totally weird, as you have seen. And it will do the same with the zooming and rotation actually. Okay, the zooming part would be now our goal, which is actually pretty simple. We have another term with something zoom, with the zoom part, but we said we don't just want to zoom in X and Y direction like that, but we want to scale the zoom factor depending on our coordinates, which brings us back to this here. So basically the relative coordinates here are what I'm looking at. So we want to have in the upper left corner, we want to have this -2, -2, in the upper right 2, -2, and then in the center we want to have 0, basically. How do we get that? Well, the formula for that is pretty straightforward. We can just take our current x-coordinate and we subtract the number of pieces in the x direction divided by 2. This will give us the -2 in the left, on the left column, the 0 in the center, and you can just put the values in here because we have 13 pieces. So the very left column will be the 0th column, so we will have 0. Let me write this down. We will have 0 minus number of pieces is 13 divided by 2, which gives us 0 minus 6, which is, because 13 divided by 2 is 6.5, but it's an integer division, so we get 0 minus 6, which gives us a -6, which is exactly what we would expect in a setup where we have 13 by 13 tiles. On the other hand, when we are at the center, we will have the 6th element minus 13 divided by 2, so we will have 6 minus 6, and that equals 0. That's at the center. Perfect. That's exactly what we want. And at the other end, we will have 13 minus 13 divided by 2. That's 13 minus 6, which gives us a 7, I would say. Actually, we're not going until there, we're going to 12, of course, because we have this less than, as I just said. So we go to 6, which is fine. Okay, so this formula works. This will give us exactly what we want, and the same, of course, and we need to multiply by that. We will do the same with the y-coordinate, y minus num pieces in y direction divided by 2. Having that should already give us a zoom effect, and indeed it does. I can stop the zoom by pressing Z. I can reverse the zoom, which copies from the border, which gives us a weird result. Or I can zoom back in, and I can even stop the shifting, the jittering, which gives us another interesting effect, and we only get the lower right quadrant producing stuff because of the way that we set the random pixels. We can shift them a bit more to the up and left, and we will get noise all around. Let's do just that. Let's say we want to set the pixels from minus piece size divided by 2 in both directions. This will give us a bigger random area in the middle, and then we get a very weird tunnel-like thing, but it's still something zoomer-like. And if we jitter it around, we get a more noisy picture here, a little bit more noise to the upper left. I'm gonna stop this before you get some epilepsy or something. Probably should put up a warning in the beginning of the video. Yeah, I'll do that in post-editing, post-processing. And yeah, that's basically the zooming already done. And the last bit is not that much more complicated because it looks very similar. As I said, we have the rotation. It gets added on top. Probably gonna break the line here so you can actually see the stuff. Times something very similar, something exactly similar, except that we will swap the Y and the X part. We actually have to use the Y coordinate here to do the actual rotation. So it would look something like this: Y minus num pieces Y divided by 2. And yeah, we're missing a closing bracket. But we actually have to do the negative of that, so we need to subtract this. You can try out without, but it will look not correct. And the same, of course, goes for the X part, but there we have to do the plus to get the rotation and use the X coordinate, obviously. So that's that. And when we start this, we already have our Dweezil zoomer. We can make the center emitter a bit smaller or something. I will now stop the rotation, first in the other direction, and now we have only the scaling. We can also stop the scaling or zoom in, depending on what you want. But now we'll turn off the jitter and turn on the rotation. And then you can actually see how this whole thing works, especially in the center. You will see in the center that we have an octagon shape where the pixels get shifted around. And if you look closely, there are a lot of tiles. In the outer regions you can't see that because they are so fast rotating that it's hard to make out, but it's an approximation to a true rotation. And that's what this whole thing is about. And without the jitter, it doesn't look quite as pleasing. Turning on the jitter makes the whole thing much more fractal-like. And yeah, this is already the whole deal, actually. It's a very simple approximation to zooming and rotation. The only magic here is the way we compute the source coordinates, and that we have to reapply the jitter if we want to have this fractal look on the way back to the frame buffer, actually. If you don't do that, then everything explodes. You can take this code, play around with the variables a bit. Be careful, because it's very easy to jumble up your whole memory and crash the emulator, but it doesn't matter, because you can always restart. We will revisit this thing and try to optimize it more and pick a very nice video mode to really draw this efficiently. Something that is very well fitting and which is interesting and which we haven't talked about yet. But for now, this is it. I hope you enjoyed it. Post any questions down below. I will link to the source code as usually. And if you want to support me, you can do that. I'm very glad if you drop a visit on Patreon and consider joining. Or you can also use Ko-Fi or a direct PayPal link, so I can do more of these videos basically. And if you don't, just leave a like or dislike depending on if you enjoyed this video, and definitely leave a comment. Subscribe if you haven't already, that's always helping, and I hope to see you very soon. So until then, have a nice time.